All right. Hello, everyone, to the afternoon session of today. It's a pleasure to have Murzin to come up with the next talk that he's going to deliver on Wolfram model tools and technologies. Thank you, Nick. Go ahead.
All right. So, well, if anybody have some questions from the yesterday's talk, I'm happy to answer those. But if there's none, I have a different notebook to share, which is basically I want to talk about like different toolings that we have and like related to WPP and just general Wolfram language tooling that can be useful for during development of your project. Like the first I just want to talk like a basic functionality in the Wolfram language that probably everyone's gonna use at some point. It's like just starting from graphs, right? Because probably everybody knows what graph is, but how to actually construct some beautiful visualizations and how to generate some particular graphs and how to customize them. Usually there are a lot of questions about how to do it. So we're just gonna briefly talk about how you can customize graphs in general. Right, just graphs is just you can construct it by specifying vertices and edges. That's pretty clear, right? You can generate some random graphs, but in order to customize those, you have to know that there's a certain types of annotations you can use for vertices and edges, right? The two things in the graph that you can customize, and there are different sets of annotations for vertices and different sets for edges, right? This is just one. The most common ones. You can specify size, styles, and arbitrary shapes. You can customize those so that you can draw the vertex in the way you want, for example, right? There are some common things. There's a multiple layouts you can use. Like some of them are not even auto-completing. Like this gravity embedding, it's not, for some reason, it's not an autocomplete, but it looks pretty fun. It has some nice curved edges. But this is just for the random graphs. But there are a bunch of others you can use just to customize how it looks like. Or you can just set your vertex coordinates by hand, either by writing them down, or there's like nice function that I have to just if we have this define this graph, right? And if you want to customize it, you just call this function. Maybe you make it larger by specifying a different size, maybe 500. And it just allows you to drag vertices around. So as soon as you drag it around, because you wrapped your graph with this dynamic thing, it actually changes under the hood. So this G is now whatever graph you've been dragging around here. So if you regulate it every time, your actual graph sets those coordinates inside of that. So that's how we can, like, if you don't like particular automatic embedding that assigned to a graph, you can drag around them so that it looks nicer, right? So that's nice trick. Obviously, you can customize all the labels. You can put them inside the vertices, all the sizes. You can style each individual vertices differently. Like I don't know, like set one of them in a different color, for example. You can do some customization for edge styles. For the edges, like its style, you can customize the arrows, like the size of the arrow, or the position of the arrow. You can like put it in the middle, because by default, I believe it's not, right? It's like towards the target of the edge. And you can also make it very large. Maybe that's too large, right? Or make very small so that you can basically disable all the edges this way. Or you can just customize an arbitrary shape for your vertex. Like you can usually do it like this. It's usually like do inset, which is a graphic primitive, right? And the function usually depends on three things: is the position of the vertex itself, and its size. So when you want to customize it, you have to take it into account. But inset already takes the position and size as one of the arguments. And here you can just do whatever you want. You can make pretty much the custom graphics. But this option is very useful when you do the framed things. Without this option, your edge arrowheads can bleed into your framed insets. So that's like one of the tricks which is very common for graphs. You set this performance goal quality, then it automatically will compute the boundaries of your vertices, and so take this into account when the edges are rendered. Yeah, and there's more tricks you can do. Like, yeah, this is just, you can even put some 3D graphics in those shapes if you want to. But okay, maybe you actually want to know more about not the graphs but hypergraphs, right? So Cowers already told a lot about that, but in more now we're gonna deep in more into hypergraphs in more detail, like dig deeper into how it actually works and how we can customize hypergraphs, similarly how I just showed you can customize graphs itself. Right, there's a packlet, right? That's how you this is the latest version. You can install it either from the repository or the latest one from from that using that link. This is like sometimes it's more up to date than in the repository. So if there's any bug encountered, please tell me. I'm gonna fix it as soon as possible. But basically, that's how you load it if you install the packlet. Now you have this hypergraph function that allows you to construct hypergraphs. So it's basically almost the same. Oh, it's syntax. You can use the same kind of syntax as graphs, but by default, the edges are unordered, right? But you can still make them unordered by using the arrowhead. But obviously, hypergraphs are more general because you can make more high arity hyper edges, or you can unary edges, or even make like a zero unary edges, which is just like an edge that doesn't have any vertex, right? So this is like very similar to graphs when you style it like this. For the hypergraph, the graphs also allows you to tag each edge like this, right? For example, if you want then say that edge labels are tags, you can actually do this because this tag is tagged and you can actually visualize it this way. But for the hypergraph, you're allowed to basically do the similar thing, but in order to tag an edge, I guess you can do it like this. Okay, there's some subtlety because we are tagged it. Now we have to specify it's explicitly here. And there's some, yeah, you have to do it like this. And I guess edge labels also would work. I'm not even sure whether this particular option can work. Let's try it. Yeah, so basically almost the same as graphs. I tried to make it as close as possible, but it's still more general. Like, for example, this edge symmetry just says that all of the edges going to be ordered, even though by default it's unordered. Then doesn't have any edges, arrows on the edges. Okay, we have some styles, and not lots of them. Those are basically some substitutions for all of those stylizing options that I have. Like Wolfram model is the default, I think, if you don't specify any plot theme. Just looks like a usual rendering of hypergraphs that we have in the physics project, but there's like some dark thing, and the automatic is just like some random colors. The default color scheme for that Wolfram language uses on the hood usually. All right. Okay, if you don't like these visualizations, there's some other options. You can use the Wolfram model plot. That's how we render hypergraphs in the physics project usually, right? That's just to compare how they look. They have some differences and how edges with with loops are rendered. For example, this one, we prefer this kind of petals, and also some curviness to the edges when they have high edges. Okay, but there's also two nice functions in the repository for completely different rendering of hypergraphs. If anybody want to use those, there's an option too. All right. Now, if you have any specific request of how to do some particular thing right now, maybe you already encountered it in your project at this point, you can ask. We can try to live code it right now. All right. But if there's no any particular requests about hypergraphs and graphs, we can move forward to the Wolfram model. This is just there's going to be a lecture by Max Pixcon of the offer of this packlet and the Wolfram model functionality later. I think it's tomorrow, right? I think it's tomorrow or after tomorrow. So I'm not going to spend too much time on this. It's basically just the basic functionality to actually rewrite the hypergraph and do it for multiple steps, just to run through it, just to see what it does. Right? You specify a list of hypergraph rules, initial hypergraph, which can be automatic. It just extracts, I think, the left-hand side, and how many steps you want to write. And it produces an evolution object, which you can query. It contains a bunch of options, properties that you can query. Like the most trivial ones that you probably need is the list of states or the hypergraphs at each evolution, at each generation, I guess, after each rewriting event. And that's how you can plot them. Well, let's actually try compare this to our hypergraph. It's a little bit slower because it like involves some weird reshaping of the edges, but just to compare the differences between visualization that we have, especially in this loop things. But that's just was our choice. What's this? What's this vertex table? No idea. Yeah, that's how we do. How do you visualize the hypergraphs? But this is the most important properties if you want to actually use in your project the evolution object. Probably you want to extract not just the hypergraphs, but some information about events. And in my experience, like these options, the only thing you would actually need. It's like you can extract all the events, which is just information about what hyperedges were the input, I believe, or the indices or something like that. I actually myself don't particularly remember what this is. This is, I think, just if you have this list of all the input hyperedges, these indices tell you which ones are, like, for example, this event took hyperedge number 3 and number 5 as an input and produced hyperedges 6, 7, and 8. And that means basically you have to extract it from this list. So that's how you can extract all the events and do whatever you want out of those. This is just to compare how it looks in 3D, I guess. It's not perfect, but we also have an option to render those hypergraphs in 3D. But anyway, okay, the next tool, this is like the Wolfram model is the evolution of hypergraphs is applying rewriting rules in some particular order. So if there's some conflict of how to apply the rule, maybe there's the same hyperedge or overlaps and the same rule can apply to multiple on that hyperedge in multiple ways, or they're just simply more rules. And there's some ambiguity. The way to do it is actually use multi-way system, and there's a classical function from the beginning of the Wolfram physics project as a multi-way system that also allows you to run the Wolfram model for multiple steps and draw all those kind of graphs that we specify. For example, the evolution causal graph not just contains each hypergraph and all the possible transitions, because now there's ambiguity. It's not just one path of rewriting that Wolfram model does. It contains all of them and also draws the events themselves. So that's why it's like some form of bipartite graph, I guess, of states and events, and also two kinds of edges. There's always an edge from state to event, from event to state, from the event to state when the state was produced by an event, and also the causal edges that also show the causal dependency between those events. And there are more of those. There's like everything is in the documentation because this is a source function published in the repository. If you click on this information, you just get to the site with all the information about it. You can read of all the possible properties you can extract and compute, all the different graphs and how you can customize the multi-way system. It's not just hypergraphs. You can do the substitution system with the string rewriting rules, even cellular automatons, and there's like many types of multi systems in the repository already, not just this general multi-way system, but like you can do the group ones, just like some modifications of the original one, and how you would construct it. All right, but like a more modern tool that I was building, which kind of tries to specify the same kind of multi-way systems, but in a different way. In a different way, how we specify it slightly different and also in a different way how it works under the hood. And I probably will tell more about how it actually works, because it's quite interesting. It's again the same, very similar to the hypergraph package. It also lives in the repository. You can install it either from the repository itself or there's a development link. That's how we load it, and that's how we construct the multiway system, right? You again specify a rule or a list of rules and some initial hypergraph, for example, and it constructs not produces some property, but constructs an object. So it's in a way similar to the Wolfram model above that constructed the evolution object. Here just constructs a multi-way system object that has some type. And basically nothing else, just like some held input and some things under the hood that it holds. I'm going to talk about what it actually does under the hood later. But now it's like automatically determines what type it is. Here it says that it's hypergraph because it just list of lists. So that's how it knows that it's a hypergraph. But there's, I guess, do I have an example? Maybe later. But now you can query, after you construct this object, you can query a bunch of properties. Ask whether there's actually a list of types of graph, for example, that you can construct.
I would tell you.
Yeah? Is it a question or just random mic on? Okay. So, for example, the evolution graph is just, for example, if I don't specify this option, it just means they can apply the rule 2 times. So there's a lot of overlaps. So it doesn't perform any canonicalization by default. Like there's a lot of duplications. It means that you can compute this hypergraph on this hypergraph, given these rules in many ways, right? There are multiple ways to apply this rule to this one, and it records everything. But then there's like a canonical state function, which some built-in values that you can specify, like full canonicalization means essentially you run the canonical hypergraph under the hood, and that's why it collapses all the equivalent hypergraphs into a single one, preserving all the edges, right? So that you can actually do some counting if you prefer. And similar to the resource function for multi-way system, it also has the evolution causal graph, which looks very similar, maybe a slightly different rendering. But again, you have 2 types of vertices for states and events, causal edges, and evolution edges, I guess. Well, here is you can there's some additional tricks that you can apply. For example, the method automatic, because it determines automatically that it's a hypergraph, but when it applies some rules, you can actually do some additional functions and perform some deduplication and canonicalization yourself. This is just it's a bit already some advanced example how you can use some. It's not. I'm not sure even it's documented how you can apply arbitrary function to the matches under the hood. So let me actually try see what it takes as an input. So here you can see that the match, what I define as a match, is some kind of association of positions. And the output is just a list of hypergraphs, and you can process it how you want. Here, just deduplicate it by canonical linked hypergraph. The linked hypergraph is just a special data structure, which I'm probably gonna explain later what it is. That's the main data structure that this packlet is running on. Okay. Oh, the way you count, if you like construct this evolution graph and you canonicalize, one way of counting of all those edges is just there's convenient resource function that you can do it. It's like simplifying the graph, but it also assigns weights to all the identical edges. So it makes a simple graph, which is the graph without multi-edges, but it preserves the number of edges into weight. So it stores it into a weight. So if you label the graph with its weights, you can see that those are going to be the original counts for the edges. So that's the only subtlety there, that you have to untag it, I believe, because it doesn't work with tags for some reason. Okay, what other examples I have? This is I think this is the same thing. just apply to evolution causal graph. Again, all the causal edges are preserved, but now we're canonicalizing not just the states, but also events. If you don't custom canonicalize them, I guess you preserve every possible event there, which is like a lot, because you have an event for every edge. That's basically preserving all possible ways, as I said, to rewrite that hypergraph to this hypergraph, and they all just duplicated there. So there's a way to canonicalize them. If you actually, by the way, if you mouse over those events, you'll see the actual underlying structure and all the information that is those events are storing, like which hyperedges are taken as an input, which hyperedges, not hyperedges, vertices of the hypergraph basically are the input to these events, which are the output, which rule are used, what are the position of hyperedges, and so forth. There's a lot of information in the event that one can potentially extract. Okay, this one. Yeah, this is again the counting, but now you also include the causal edges too. Right, so a lot of more examples. But I guess just in general, the multi-computation can be better understood not with hypergraph, or not even strings, but with just general expressions. Like the Wolfram language is built on top of 3 structured expressions and rewriting rules. Those are like the basic programming concepts in the Wolfram language. So maybe the concept of multi-computation itself can be better understood in those terms. And we have like Steven wrote a blog about how this expression evaluation and concepts from the WPP correspond to each other, like just what running evaluation and evaluating expressions and how the events of rewriting those expressions, how can construct those and how can generate causal graphs and how they basically correspond to time and basic physics of the WPP and all that. All right, but then there are 2 functions that are basically the workhorses for this kind of evaluations that you can use this. There are multiplace, which is very useful for expression rewriting, and even mathematics, or basically rewriting of theorems and lemmas and axioms like that, thinking of them as rules. That also was a main workforce for this kind of work with mathematical axioms, because besides just doing a simple expressions, it has some different kind of substitutions which are very useful when you're working with variables, and variables are very useful when you have mathematical theorems, because their variables represented by arbitrary patterns are very important. So this kind of methods are very useful for replacing lemmas and deriving new lemmas. That's why this is a good function to exploring this kind of ideas. But for now, just to understand what multi-computation is all about, I just think of the simple expression in the Wolfram language. Say that's like, for example, this one. When you just compute the sum, you can do it. Yes, it's produced 10, but you can do it in the 2 very different orders of evaluation. You can evaluate this parenthesis first, or this parenthesis first, or you can evaluate them in parallel, right? And basically, you can assign for each of those evaluations a particular event, and you can conveniently do it with this function, which tries to construct the whole causal graph for that evaluates an arbitrary expression in the Wolfram language. It has some limitations, but for some simple expression, it works nicely. Like this one, you can see that it's like in physical, in Wolfram physics project terms, you can see that there are 2 space-like separated events. That's because they don't have connection and the causal edge between them, but they cause a single event. But that which means they can be evaluated in parallel. There's no ordering, so either this one and this one can be in the first one. And for example, if you make a function like a Fibonacci, a recursive function that depends on itself, in the Wolfram language, all of those definitions, when you basically define a function like this, it boils down to defining some kind of rule on the hood, and that's how different kind of values. Wolfram language has some different kind of values for symbols. When you have the definition like this, which means you basically create a new types of rule, which is called a down value for this particular symbols, and you see that it actually under the hood is just a rule. That rewrites this expression into this one, where n is some kind of variable. And by default, because I haven't specified a base case in this case, of course, it's like it relates to a recursion limit because it never terminates. So you can see that it tries to expand this Fibonacci term 1024 times by default, and it's like it just produced an error or message. But you can, in the trace causal graph, you can terminate earlier. There's like some limit or upper bound for how many internal events you can generate to construct the causal graph. So it's actually would produce a finite graph like this. And you see that there's like all the kind of events happening that are generating negative numbers, right? But you can see that all tries to do to always to under the hood Wolfram language always evaluates the left innermost expression, right? So all the events happening on the left-hand side of the expression, and that's like its order. So that's why the causal graph is always going to be, unless there's some parallel evaluation can happen, and Wolfram language by default doesn't do it. There's always going to be a single event, so it's always going to produce a path like this, right? Here it was because it terminated. You can actually recover the events, and you can determine or infer that they were actually space-like separated, and you can construct it. But if it doesn't terminate, it's usually going to be just a path like this, because you can always going to be a recursion code will always look similar to that. That's why there's like a separate function that tries to take this form of evaluation into account when, as soon as you have a rules defined, which is basically works like any kind of multi-way system, but it tries to be more clever and derive those rules automatically from the definitions. So that's why it's called evaluate. So it's multi-evaluating this expression, and you just again have some upper bound on how many times to apply the rule. So it's like a multi-way system, and you function, but you ask some property, define some additional options. For example, like evaluating plus when you actually have an expression that has some additional integers, so that you can explicitly move it through the kernel so that it also evaluates, because it's not explicit in the rules, right? That's the only rule that we have. We know how to rewrite the Fibonacci term, but we don't have a rule to add integers. So that's why we have to explicitly say, okay, as soon as you have additional integers, just go for the standard evaluation. And that's how you can see that if you run this multi-way system 2 times, so at first it just uses the definition, but then you have multiple ways to continue your path, like 4 times. You can either evaluate this addition, right, because it, or this addition, or you can expand the Fibonacci again, either the first one or the second one, expand the definition. So that's why it's a multi-way evaluation. It tries all those possible rules in all possible orders, and even those that have some ambiguity, and so that there's actual branches. Like here, for example, for this simple expression again, there's the most maximal graph with all kinds of types of edges that you can imagine, right? So like you have and also vertices, you have events and you have states, you have causal edges, you have evolution edges, and you even have branchial edges. And you have branchial edges here exactly because between events. So it's like causal branchial edges. It's a little bit different. That's why they have this dashed style. Those just say that those events are overlapping in some sense, right? Here it's a little bit subtle. You would say, well, what's the difference between this event and this event? They both try to evaluate 1 plus 2. Why do you need 2? And it's subtle because here the pattern is just plus. We're not constraining it to evaluate plus of integers. So even this intermediate plus is also evaluated. So if you just ask a Wolfram language to evaluate the outermost plus like this, it will try to evaluate this most inner part first. So that's why evaluating this plus and evaluating this plus generate the same event, because if you evaluate the outermost plus, evaluating this one is just also the next step. So that's why it generates these two events. A little bit subtle, but that's the kind of things you can expect from evaluation. Yeah. Right. This is just another example, a little bit more simpler, just to see what's going on. You can define a function and try to evaluate it. Again, there's a simple branch edge, just because you can evaluate either the outer f or the inner f, right? And they overlap, and that's why it's like looks like they space like separated, but we draw the branch edge between them because it actually has to create a new branch, because you can't evaluate it in the same branch. You either do one or another. And just to see just a comment on this different kinds of values, a little crash course on Wolfram language values. There are actually 4 types of them, and this nice example shows all of them at once. I can see that there's like if you define it and try to use multi-evaluate on this expression, this is all the possible ways and all the possible kind of rules you can apply or evaluate at this expression. Like and this is down, sub, up, and on. Those are the 4 types of values that you can evaluate. For example, the on value is the most trivial ones. It corresponds to this definition. So when you just assign something to a variable, what it does under the hood, it defines the own value for that variable, which is again just a rule, right? It says, okay, if you see x somewhere in the expression, it should be rewritten as 0. So that's what our own values are. Those are the rules assigned to a symbol, to a simple symbols like x here. The down values you already seen. Those are just the rules that are usually defined when you create definitions like this, like the usual functions, for example, with arguments. The up values are trickier. They are created when you define things like with this sort of thing, which means you are, which basically the same as a down value, but and it creates a rule, but what different is for what symbol it creates it. For example, the up values, when you define it like this, it creates the up value not for the plus. Well, if you will create this without this symbol, it would create a down value for plus. But if you create it with this one, it means you have to look deeper into the definition, and in this case, it would create actually not the down value for plus, but for the up value for minus. Right, so this is the rule that it creates. And this is like the useful thing to know about when you want to override some system functions, for example, that work on your types of objects. Because now if this was the system function like actual plus with the capital P, and you wanted to teach Wolfram language to add some objects, like maybe your hypergraphs, right? That's how you would do it. You would create like one hypergraph, another hypergraph, and you create an up value for that. That would define an up value for the hypergraph and not the plus, because you're not allowed to modify the internal symbols. So that's what up values are useful for. And sub values is just the thing to have when you nest these brackets, right? As soon as you have these operator forms, that's where the sub values are created. So it's not very interesting, but it's just as different types of rules. So, okay. Do you have any questions? I'm losing people, I see. Okay. Next, I want to talk about some internals of that multi-computational packlet, because there's a special object that is a workhorse for the whole packlet almost, and it's on its own, but it's very interesting. It's like allows you to create sort of like, well, it allows you to do more than one thing, but you can think of it as a first approximation as just a superposition for different kind of values, or a container for different values, right? We call this object multi, and it's like it's simple to explain with examples, right? as a container of values, multiple values. So it's like a superposition of this list. So you can represent it as a placeholder that stores some values under the hood. Right? For example, if you create two multi-objects, one of them contains 3 values, is a superposition of 3 values, another one is superposition of 4 values, and you add them together, that automatically creates a new object that has like a outer product of those. So now it's a new multi-object that is can be like a product of one value, one multi of 3 values and another multi of 4 values, which is in total is 12, right? 3 times 4. Or you can like use arbitrary expression. You can use this as soon as you use the multi in arbitrary expression in the Wolfram language, it's just gonna propagate to the outer layer and create a new multi-object. So it doesn't have to be plus, it can be just simple list or like anything that is not held. So the only way you actually have to store it as multi itself without doing it, have to like hold it, something like that. So that's why when it's held, it's never gonna propagate. But as soon as it's like released, it's gonna create some. Yeah, it doesn't matter. I wonder actually what's gonna happen here. Yeah, it's gonna create a sequence in this case, which is very weird. And those multi-objects has a lot of properties. And here is just how you can extract all the possible lists of results if you just would substitute the corresponding values in those placeholders. So how to actually extract those 12 values out of the object. You just evaluate them, or just you can evaluate it by holding. It's kind of delays all the evolution so that you can see that actually what we are adding instead of immediately evaluating them, which means that you can kind of use this object as a lazy storage. Like for example, if you have a very large expression, like with million elements, and you have another one, large expression, then you create a tensor product of those, outer product, which like has as a product of those values. So it's a very large object, right? You can't really problematic. It's going to be problematic to actually store it in memory, but it's still you can create this kind of object easily because you don't actually evaluate them immediately, but you can, for example, ask for first 10, right, out of those trillion values, right? And you can hold them. But you can also do but there's some more useful properties that this multi-object has. Like yes, I showed that you can just query it. You can create a new functions. Like if you use the same object twice in the expression, it's going to treat it as a product. But if you don't want to treat it as a product but do some kind of element-wise thing, you should use this property by applying like some function to each value. So in this case, you multiply it 3 by 3. That's why the 9 values in total. But when you use apply, this is still, you basically treat those as parallel. And that's the difference between this parallel outer product, or this outer product and this parallel application. You basically store, you can see these values contain all the information of those values and the position in the expression. So that's how it's implemented at the hood. You need to store where the position in the expression for each of the values. So if you have an outer product, it means that you have 2 positions, like these 3 values are located in the position number 1. These 3 values are located in position 2, 2. So in this placeholder. So we just store the position of placeholders. But if you have this parallel application of the same function, it means that you have this 3 values, but in multiple positions, right? So that's like a simple data structure, how you can reason about this. And they evaluate in the corresponding expressions like this. But they also can generate, but when you define all of these objects, you can also generate a type of events, right? You know that the event of evaluating, like this set of placeholders evaluates this expression, If you have a outer product, it evaluates in a little bit different way because you can evaluate either one or another. That's why your placeholders are preserved. And when you have these events, you can basically build the edges. And that means that multi also has a bunch of graph properties similar to any multi-way system. As soon as you define all of these elementary types of properties like constructing events and edges, you can think of them how to construct generally, how to construct graphs and causal graphs, right? And that's the properties that those multi-objects have, right? The multi-evaluate, by the way, just another property that doesn't produce a list, but produces another multi-object, but with the values, with new values inside of it. And that's like just example of graphs that you can construct out of it. Even the branch of graphs. This is just an example when you can use sequences. And that's how you can mimic some form of numerical multiway graphs, I guess, numerical multiway systems by just adding a rule. So, or maybe I should have delayed this example for later, because that basically shows you that multi is not just about storing some values, a list of values, but you can also define a rule, and that's how it basically can define infinite infinite number of values, because your rules acts as a function, and or not the infinite, or I guess just delayed values, because you uncomputed values, because you have to actually apply the rule to derive the values before. So it's not explicit, it's like has to be computed first. So instead of storing values, you can store rules, and that's how you can derive the values. So that's a different usage for those multiness. I was going to say to talk about them here. So yeah, so instead of explicit list of values, this multi-object also can just store the rules, and instead of values now you have matches, right? So if you construct this multi-object, the matches essentially tell you all the possible ways you can apply the rule to your expression, which can be also arbitrary. It also tells you about where the position of that rewriting can happen, what type of matches can happen, because it doesn't have to be an explicit rule. It can also be, again, like the multi-evaluate above, it can also be some value, maybe predefined function in the Wolfram language. That's why instead of rule, it can be like sub, down value, up value, sub, or all values, and some bindings of variables, because when you apply the rule, usually this x is bounded to some sub expression in the expression. So that's why this association is for. Basically, there's all the information about the actual match and the result, which is a held expression. So it's never evaluates the expression before you actually need it. Right? That's how you can apply all the rules and see the held ones. If you don't held it, it just produces a new multi with the values that you get after applying all those possible rules. And basically those rules allow you to create this multiness, which before we created multiness by just explicit list of values. Rules allow you for more different types of multiness, basically multiple ways of creating multiple values, so to speak. One of them is obviously you can create a rule that explicitly just outputs multiple results, right? That's maybe, well, the easier one is just having, of course, multiple rules. But another one is having a single rule that produces multiple outputs. That's another way of creating multiple results. And here's just a similar example, right? An obvious one. Again, you can also use these objects as before when we were constructing new multi-objects from other multi-objects by just using them in the expression. Here, for example, if I've created this object with the stored rule like this, if I just use it in this expression, like multiply this object by 10, it knows about that this 2 is the only place where my rule has to be applied. It remembers it, and as soon as I evaluate this new multi-object, that's what I get. My rule only applies to the 2, right? It kind of knows about where it belongs. And you can construct all these graphs out of those multi-objects. Another way of creating multiness, multiple values, it's not by explicit list of values on the right-hand side of the rule. We can actually use pattern matching. Wolfram language has a powerful pattern matching primitives, which basically allows you to bind your variables, these pattern symbols on the left-hand side of your rule in multiple ways on its own. So in a way, even if you create a single rule with a single output, it still can represent multiple matches. So here I've created a multi-object, right, which contains this triple underscores, triple blanks, which basically corresponds to arbitrary sequence. That's why this left-hand side can match against this expression in 2 different ways, right? This x can either bind to this 2, because this triple blank sequence can allow to match against an empty sequence, right? And this can bind to 3. So basically this x can be either this one, or it can be this one, depending on which those triple blanks are bounded to. Right, so that's why there are 2 matches. You can see that now we have 2 outputs, not because there are multiple rules or there are multiple positions. There is a single position, a single rule, number 1, but there are multiple bindings. Basically, we can bind x in 2 different ways. That's like a different way of creating multiple values. And again, in the same example, if you take this multi and multiply it by 10, that produces a new multi-object, and it knows where this rule belongs to. And it never evaluates, and it always tries to delay the evaluation as much as possible. So these echoes are still there. It stores them. It never leaks until you actually start try to create a new multi-object. That's why it's like, while producing these new results, it evaluates this echo 2 times, and this creates it 2 times because why? Because there's a I'm not even sure why. There's some subtle thing that I forgot about. Okay, let's not worry about it. All right. Another mode of operation, you can say, for that of rewriting rules is, instead of like having multiple outputs, multiple ways of to pattern match, you can, given some arbitrary expression, you can also pattern match against different positions at the same time. So that's what I mean by multiple inputs for the rewriting rule, right? And you can also operate this kind of multi-input rewritings in different modes. That's why you can read all about it in the multi-replace function. That's where those modes are implemented. So there are multiple of them. So you can basically, it tells you how which sub-expressions to consider. So when you write a rule that takes multiple inputs like this, it basically tells you how to extract multiple sub-expressions from the expression, right? If it's tuples, it's gonna be allowed to match these 2 twice. If it's a subset, it's never allowed. But if it's orderless, you can also swap the order of those. If it's order tuples, I think I have the good example here for the modes. Yeah, just screenshot this. Put it here. Make it bigger. Yeah, so we can see that in this example, when you try to match, this is always the same input and the same rule with different modes, so that you can see the difference. For example, if you have tuples and you try to match double A's, it will match 4 times. So it will match against this A twice, because you are allowed to match this A and this A against the same A, right? And you can do it for this A too. This is where the last one is 4, which maps that position 3 twice. And also see that how the replacement works. It always rewrites, it rewrote the second one, the second I, but the second output got dropped. So there's also some subtleties there. right? Again, if there's ordered tuples, then free one rewriting never happened. So they have to be ordered. So one free is ordered, but free one is not, so that's why it's not there. The orderless subsets, again, this is because it's a subset, the free and 1 are not allowed because it's like a multiset then. And in subsets is basically just one possible match, right? Because those have to be at different positions. So that's what mode means, right? That's how you can match at different positions of the expression. Like in this case, I guess if you specify orderless subsets and you try to match against this expression at level 2, it will match only against 2, 3, and 3, 2, two different ways. I guess we can try it out by actually acting. Or maybe we should try this one anyway. I have implemented it here. So here you can see that we're on all the possible ways to rewrite it. And yeah, you can also specify how many times to perform the same rewriting. And you see that it like exponentially increases. And it also stores it. Well, maybe hold is not a very good example. Let me try running this without hold. Yeah, you can see all the possible results that you can produce. This multi-list evaluate is a little bit different semantics rather than just multi-evaluate that tries to nest those lists indefinitely. The list evaluate always flattens it, I think. So I'm still not, even if I wrote this functionality, I'm not still a very good user of it because I still try to find a nice function, nice implementation, not nice use case for this data structure. So I still haven't found it a good use and good excuse to use it. Okay, this kind of thing I already showed you with multi-evaluate, but here how you can use it, how you can use this defined values of expressions, like if you have an actual definitions already defined, like just defining a function, defining a variable, some up values, own values, down values. If you just construct a multi out of it, you have to use unevaluated before. Otherwise, it's going to evaluate first and just create a like this dead multi, inactive multi that doesn't have any rules assigned to it, right? But if you hold it, you can hold this expression, and it immediately determines that there are 3 different rules that can be applied to it that you just defined. And in this matches property tells you all about this. There's an own value at position 1 that rewrites x to 100 to 200. There's a down value, which is this rule for function f, and there's also up value. So even though like when you have this set of rules and you evaluate this expression in the kernel, it will always gonna evaluate the down value, right? So it finds the x, which is 100, and it just adds 1. So this definition was completely ignored by the kernel because there's some defined semantics of evaluation order in the Wolfram language, so that it always uses the first rule that it's possible, even though there's some definitions that are already present, completely different definitions. But the multi-evaluate and this multi-objects try to take all the rules into account. So that's what kind of multi-computation means in this context. So the 3 rules, so they apply all of them, even this up value, which is equal, when it says that when you have this f of x, you have to produce 10. So, and you have this result here. Yeah. So that's why even though Wolfram language is defined in such a way that it's confluent, if you don't have any side effects and all that, multi-evaluation can produce completely different results, right? So yeah, this explicit pattern is again the same kind of thing as for the multi-evaluate function, that you can just define what to produce, what kind of sorts of patterns just evaluate through the default evaluator, right? Because plus there's no an explicit rule for how to perform addition of integers. There's some internal code that does this, of course. So we have to tell, okay, you're allowed to evaluate this pattern. So that's why there's a match. If I haven't specified this option, there wouldn't be any match, and if you try to evaluate it, nothing would happen. I guess it would be. It's still gonna. It's still gonna try to move it through the evaluator, but it's not gonna register it as an event, I guess, or any match. But now we know where the pattern is, and it can also happen at like at deeper expressions, I guess. So here it's two matches. So you know that you can evaluate either this one or this one directly. All right. Anyway. So okay. Let's see what else I have here. Of course, yeah. So we talked about these two particular ways of creating those multi-objects, either by explicit list of rules here, or specifying not the rule specific list of values, or some rewriting rule, right? But you can also combine them. So if you have a multi defined with multiple values and a multi defined with a rewriting rule, if you add them together or use in any kind of expression together, now it's like a combination of two types, so you can have both values and matches simultaneously, and they behave as expected, right? If you try to evaluate it, you either substitute the value, one of those two, into the placeholder, or you rewrite your expression here based on your rule, right? So it's kind of, yeah, so it behaves as expected. You can do some crazy things with this. There's some convenient properties you can use for multi-theory, which is kind of similar to the expression data structure, express struct data structure, which just allows you to manipulate expressions without touching the main evaluator of the kernel. It just allows you to move around your sub-expressions or like replace parts of it. That's why it's like multi, because it like tries to carefully hold the expression, and there's some surgery type of properties like maybe wrap, like here, because I extracted this. If I want to add +1, it actually evaluates this sub-expression before adding 1. So it kind of moves it through the evaluator partially. So, but you can use like hold version of it. Now it applies hold and without actually evaluating the index structure. There's like more example. You can just replace things at certain positions. You can do this. It's kind of more, even without holding it. This is like because it uses this map at evaluate function under the hood. It kind of allows you, because usually, yeah, that I'm showing this what this kind of function tries to solve here. Because when you try to evaluate sub-expression in the term, for example, if you have some held expression and you want, for example, add 10 to the second one, that's what happens, right? Because I'm holding the whole expression, and as soon as you try to apply some function inside of it, it's not going to evaluate. So you have to dance around, somehow extract it and put it back or whatever. It's not very convenient. So that's why there's a map at evaluate that tries to circumvent this problem. For example, if you just do an obvious thing, it does this, but you can also hold it at some degree so that it doesn't produce this ugly thing. So that's pretty convenient. Okay, so some zoom. Yeah, thanks, James. All right, what's next? Oh, now there's just more examples of creating rules like the combinators, right? That's just the definition of SK combinators, Sky combinators. you can that's how you can use the multi to explore combinator calculus. This is just some nice graphs that you can just immediately produce given these multi objects and just the definition of rules. Yeah, you just need to specify that you also allowed to apply the rules into the heads of expressions. You also get the causal graphs with some default rendering of events, so you can see that what before and after you apply those events. Just the different ways of doing it. Yeah, those are using the binary application operator. This is using the head structures, the construct expressions, but basically the same thing. And you can you can also convert them into hypergraphs, so they can see that some nice properties of the sky calculus, that it's confluent. So whatever path of rewriting you choose, you end up in the same expression. That's the confluent property of combinators. This is causal graph expressions. The multi-way system. The multi-way system, yeah, I already showed it, but when you use this kind of expressions that contains head, like the nested heads, when you do the multi-way system, it actually you have to use a different type. That's why the under the hood data structure of the linked hypergraph that I was maybe about to show next, maybe later. Maybe we should show it now, I guess. I'm gonna skip like string examples and all that and series. Yeah, just talk about the under the hood data structure for the multi-way systems. It's basically why we use hypergraphs. It's like maybe the obvious question to ask. It's like because it's very convenient to define the notion of causality and all those within all those updating events. And by that I mean especially when you have this particular type of hypergraph, which I simply call linked hypergraph, because they have an explicit special vertex which is just called link. So every hyperedge in that representation always contains a link as the first vertex, and the second vertex is just like some special holder for whatever you want. I just call it payload and all the other dependencies that this hyperedge links to. So for example, in that representation string, a simple string would look like this as a simple linked list when all the links are explicit. So it means that the first character has an address 1, and it links to the second hyperedge which has an address 2 and stores B, right? That links into the next hyperedge and so on, which is just a linked edge with the last one linking to nowhere. So there is no hyperedge that has address 0. So that's basically this linked hypergraph representation for a string. But you can also construct a similar representation not just for strings but also for expressions or even for other hypergraphs that are not linked but just have this list of list representations, right? When you have just expression, it's basically just a tree. So this is like f is a head here, but it has two dependencies, so it links to this hyperedge and to this hyperedge, right? So it has two dependencies here, two children, I guess. Right, so in a way, there's just two simple functions that allows you to go back and forth between those linked representations and whatever was the previous one. For example, you have to specify the type when you convert backwards, of course, because the same linked list representation can be interpreted differently. It can be a graph, it can be a tree, I think, right? Or in this case, it has to be a string in order to actually extract the same thing before it was constructed. And this representation basically allows you to track the causality when you rewrite these hyperedges. So that's why I explained it now, because you'll see that when you mouse over maybe we try actually running this graph without anything. Maybe states graph. Oh, it has to be a multi-way system. Do you have a multi-way system defined here, right? So we define our multi-rules, and here the multi-way system. No, what did multi-rules? What? Confused. What's broken? I broke something. Okay, we'll just ignore this for now then. I'm gonna debug it later. But basically, if you construct this multi-way system with these rules, it's gonna convert this expression under the hood, this expression to the linked hypergraph, right? And it's gonna contain like a special constructor because it's a nested head expressions. So we have to construct them, and that's the type of linked hypergraph. And you see that the events here contain some input links and output links. So that's why it's very convenient to track the causality, because you know those links are now explicit. And it's very useful for strings. It's useful for strings because you see as a, let's do it for strings then. For example, if we just have a simple string substitution, right? You don't have to create this. As soon as you create a graph, you see that under the hood, it's like those edges or those vertices are just hyper edges with those links. And there's a problem with particularly strings has this nasty problems, because as soon as you, for example, have this rule and it applies like this, for example, right? It writes the first A and it immediately changed the position of this B, right? Because before this B, if you were tracking causality using string positions, it would be much more complicated than the links. Because here I've created a new link explicitly. It has some ugly unique symbol in it, but that basically allows me to use that symbol, that unique symbol, to track causality. Okay, now I definitely know that I created a new character there, and the link for letter B, the character B, haven't changed. So if there's like a second event, maybe like a second rule acting, tries to write it to C, something, I know that which one is, maybe it happened on the second step. Like here, I know, and I see the causal graph or whatever. I know that this event is like causally independent, and without tracking in some complicated way the string positions, where the rules, when they rewrite some first character, basically moves the string positions and it destroys the original one. So it would complicate the causal tracking. That's just one obvious implementation, or obvious, not implementation, but that's why one reason, at least, for using this linked hypergraph representations under the hood, so that you can have a common data structure for all types of computational systems. As soon as you know how to convert them into this linked representation and how to rewrite it, you immediately know how to construct the causal graph out of it, because all of those links become explicit, and you know that just by having one particular definition of what causality means. It means like the two events are causally connected where the inputs and output overlap. Like you can see that this event outputs this new unique vertex, creating a new character, and this event uses it as an input. It means that they have to be causally connected. So that's basically your criteria, and that's why it's very simple criteria, just whether input and output overlaps. Imagine making it from just the string positions. Would be much more difficult. Yeah, we have this example, strings, and there are more types of graphs. There's a nice one, maybe cellular automata, well, just a fun example. It may be more advanced because you have to it also shows, even though the cellular automaton, like this glider gun that creates gliders, even though all the cellular automaton, even these 2D ones, are technically always there's a single event, a global event that produces a new state from the previous state. You can kind of create a special type of graph, which I've only played with for the CA types of multi-way systems, that tries to separate all the causally disconnected regions of the state of your cellular 2D cellular automata state. It disconnects all the causally disconnected pieces. It basically and creates this token event graph structure when the first event is just the initial one that produced all of the 4 disconnected pieces. They disconnected because they far away in the state, so that the rule and the game of life rule does not apply to both of them at the same time. So that's why they're just 4 pieces completely independent. And the next event like takes those 2 things, because now they can produce new things, right? New game of life pieces in such a way, and you can track all the pieces like this that evolve and move around. And yeah, so this potentially can be used. Maybe there's like one Stevens block in the making about games of lives, and this kind of functionality we're probably gonna use. But it's like there's too many projects at the same time currently, so maybe later. All right, so this is like so we went through all the multi-way system, multi-computational packed functionality, most of it, I think. So if you have any questions at this point, because I think I've finished. Most of the tools of the useful for the winter school, I guess I covered. So unless you have some specific requests or maybe some problems that you already encountered, I'm gonna finish here. So thanks for listening. I'm gonna
Are there any questions for Max? For Nick?
It's a bit overwhelming. I get it.
All right, then let's thank Nick for this wonderful talk, and you'll see the material available soon as well as the recording. Thanks everyone for being here. Thanks, Nick. Let's get back to work.
Yeah.
Bye-bye.
Thank you.
Thank you.